I'd like to welcome everyone. I've just let you in from the waiting room. So just to tell you that this session is about the nuts and bolts of IMS lock management. So that's the session that you've just joined, and it will be presented by Kevin Stewart, an IMS technical support advocate. And the session code is 5AI. So I'll just go through some of the details before we start and introduce Kevin. So firstly, the session is recorded, so just bear that in mind. If you've got any questions for Kevin during the presentation, then please use the chat facility, and you can do the chat session to either myself or Kevin. Kevin is fine fielding questions via chat. So if you want to ask him a question, then do it via the chat and he'll try and respond during the presentation. And then we'll have a little bit of a question and answer session at the end if people have some further questions that they'd like to impart. So without further ado, what I'll say is, so Kevin has been with IMS for over 35 years. So we're very grateful that he's got time for us today. He's obviously a leading software advocate for IBM and has got a vast amount of experience in IMS on data entry databases, you name it. So without further ado, I'll hand over to Kevin.
Thanks, Dominic. Good morning, and I guess for you guys it's afternoon. As Dominic said, my name is Kevin Stewart. I work in worldwide technical support for IMS. I'm advocate for several big customers, including Barclays. So what we're going to talk today is about how IMS manages locks and some of the implementation details that you can influence. That's the standard disclaimer screen, so we can ignore that. So what we'll talk about is IRLM versus PI differences, basics of locking, and then from an IRLM point of view, the flow overview for requesting and releasing locks and making requests. We'll talk about deadlock and timeout with IRLM, and then we'll talk a little bit about measurement and metrics for locking. So you have two choices, unlike DB2. With IMS, program isolation comes with IMS. It does not run in a separate address space, does not require access cross memory to another address space, doesn't require any coupling facility structures. Locks are implemented in 31-bit storage, and it's a matrix algorithm, which limits the number of waiters for any lock to 63. And the 64th waiter will get an append, a 2478 append. It has instantaneous deadlock detection. If a sequence of lock requests is made that will generate a deadlock, the final request that's made that instantiates the deadlock is detected at that point and a victim is selected. There's no support for data sharing, and there's no support for lock timeout. IRLM is an independent component. Today, it's supported by the DB2 organization and not by IMS. But it comes free with IMS. It's included with your IMS database license. It runs in a separate address space, and it's accessed cross-memory with a PC instruction. And it does not require a coupling facility structure unless you're using data sharing. That's a common misconception, that I don't want to use IRLM because I need to have a CF structure and I don't have a CF or space in the existing CFs for a structure. But you don't require a structure unless you're data sharing. In IRLM, the locks are implemented in 64-bit IRLM private. So that's a pretty large amount of storage available. Unlike PI, where the 31-bit storage limits the number of locks. You need if you're using data sharing, you need a lock structure, a coupling facility lock structure, and locks are also maintained in the lock structure. A copy of the locks are maintained in the lock structure. There's no limit on the maximum number of waiters for any lock, no 63 waiter limit. And it has cyclical deadlock detection. That is, if a sequence of lock requests is made that creates a deadlock, it is not detected immediately. It's detected at an interval where IRLM goes and looks at all the lock requests and determines that a set of them constitute a deadlock. And as we'll see, the deadlock detection interval is a variable, it's a parameter that you can specify. IRLM supports data sharing, and IRLM also supports inter-system notify and messaging. People don't realize that, but that's actually something that's required for data sharing when you think about things like extending data sets going into extents, when you think about things like global database commands, synchronizing control blocks between systems. IRLM does provide a mechanism to pass messages between database subsystems. And it also has support for lock timeout. So if you compare and contrast the two, without data sharing, IRLM has some advantages. It has timeout support. It doesn't have any limit on waiters for locks. If you think about it, in a very large system where you're running hundreds of message regions, it's perhaps not inconceivable that you might have 64 waiters for a single lock. That's possible with IRLM, not possible with PI. So IRLM is more of an industrial strength lock manager. It's more suitable for large systems, really. You can have many more total locks. When you run out of lock space in PI, or you get a 775 abend or a 3301 abend, the 775 abend is taken by the person who requests a lock and there's not space available. So it may be the wrong person who takes the 775 abend. It may not be the person consuming all the locks. IRLM is a separate address space, so it's less susceptible to overlays and such from in common storage or in from IMS to the lock management. And obviously lock control blocks are probably the last thing in the world you want to have overlaid. It's accessed cross memory through a program call instruction. And again, you don't need a CF structure unless you're data sharing. The locks are implemented in 64-bit private. You need the lock structure if you are data sharing. No limit on the maximum number of waiters. Cyclical deadlock detection. And if you are data sharing, you need it. So if you're not data sharing, PI has some advantages. PI uses less CPU to some extent, and it has instant deadlock detection versus cyclical. If you have a lot of deadlocks, that can be an issue because you don't want to wait some number of milliseconds for a deadlock to be resolved. Lock granularity. The difference here is that PI will allow concurrent access within a single database record. You can update different child segments of the same root from different dependent regions with PI. You cannot do that with IRLM. IRLM gets, in an IRLM system, there's a wrap lock that prevents this. But how important that is debatable. It's probably rare. We have never seen issues with it when people convert from PI to IRLM. So overall, the IMS recommendation is to use IRLM. It's an industrial strength lock manager. PI's day is past. PI was intended for smaller systems without data sharing. Even if you're not data sharing, we recommend you use IRLM. You don't need a coupling facility structure. It eliminates 2478 events, allows an order of magnitude more locks. And as we'll talk about later, it has a very nice feature called lock timeout support. And whether or not you turn it on, you get metrics in terms of lock weights, long lock weights in SMF 7915 records. They're always produced with IRLM, assuming that you have the ZOS system set up to receive them. Optionally, you can turn on a wait or timeout like DB2. We'll talk about that. Reliability, availability, and serviceability. Locks are kept in a separate address space where they're less vulnerable to overlays and damage. From a serviceability point of view, IRLM is actively worked on. It has component trace, which is useful for diagnosing problems. PI doesn't have any of that. From a conversion experience point of view, a lot of people have converted to IRLM on the path to data sharing. Others have converted to IRLM just to get the function. But the main reason that people go to IRLM has been, of course, for data sharing. And in our experience, very few have any application issues. On deadlocks, a few customers have issues. You can set the IRLM deadlock cycle time quite low with current IRLM, and the cost is CPU. Deadlocks are already pretty expensive. When a deadlock happens, the 777 ABN takes down the program controller TCB in the message region. It collapses, it has to reattach, has to go through and reload the non-reentrant preload list. This is an expensive process, and the message region is out of service while that happens. If the reason you're running PI is because you have a lot of deadlocks, generally speaking, you're better off to fix the deadlocks. They have a cost even in PI. So now we'll talk a little bit about the mechanics of locking. What's a lock? A lock is an arbitrary byte string that represents a resource. Usually the resource is a database record or a database block, although not always. There are locks on other things. The DB identifier is a global DMB number that's assigned by DBRC when you register the database to DBRC. If it's not, if you're not in data sharing or the database is not DBRC registered, the database identifier is the local DMB number, which is essentially the sequential number of it in the sysgen or the import that created the database. Additional data that's in the lock, it's a lock. There's a lock type. It's fast path locks, dataset busy locks, grid locks, etc. There's usually a data set within database identifier, usually a relative number. Examples of that might be, partition for HALDB, a DDB area, or in multi-dataset group databases, the dataset group. And then, of course, something else to identify it is usually the RBA or the key. And there's some other examples, other data that sometimes goes into locks. Here's an example of a full function lock. The 09 is the length of the string. The 01 is the dataset ID. The D7 or P is a type of lock. And the 8001 is the global DMB number. So that would be, in this case, is the first database, right? Probably the first, it's either the first database registered or the first database defined if it's not registered to DBRC. And this part is the identifier, potentially a key in this case. So IRLM doesn't know or care, or for that matter, PI also does not know or care what this string represents. And these lock strings are the same for IRLM and PI. IMS's internal logic produces these and passes them to the lock manager, be it IRLM or PI. It's independent of the lock manager. An IRLM doesn't know or care what this string is. And associated with a lock is a level. That's part of the request when the request is made. And both IRLM and PI implement levels. It's not as simple as just share and exclusive. Here's a matrix that shows it. Lock level 2, for example, read is compatible with erase and with share and with update, but is not compatible with exclusive, as you might expect. Erase is compatible with erase and with read, etc. You can see how it works. For people used to working with FastPath, FastPath actually only uses share and exclusive, but full function uses a more complex set of locking. But from the lock manager point of view, all that's important is this table. It knows that a level 2 lock for the same lock name can be shared or granted concurrently with another requester for the same lock, but for example, an exclusive one could not be. So that part is the table is part of the lock manager implementation. So when you make a request to IRLM, you have to pass a little more information than the lock name. You pass the lock name and a lock hash value, and it's the responsibility of the database manager, IMS or DB2, to hash this variable length lock name to a 4-byte value. And you have to pass the lock level, and you pass the owning subsystem, which would be the IMS ID, whatever. And within the subsystem, an owning work unit. Usually for IMS, this is the PST address. The PST represents the dependent region. Sometimes locks are held by internal processes inside of IMS, like output thread, and those have an associated system PST address. And you also pass information about the request type, whether it's conditional or unconditional. Conditional means that if the lock is not available, give me a return code. I don't want to wait. I just want to know whether I can have the lock or not. Unconditional means that if the lock is not available, I want to wait. What do you get back from a lock request? You get back a lock token. It's a 4-byte value that represents a granted lock. And you need that. You got to keep it because in the future, when you want to change that lock, alter it, or most likely unlock, you need to supply that token to be able to unlock it. And you get a return code. If the request was not successful, the return code indicates why the request failed. So request types, obviously there's lock and unlock, which are self-explanatory. There's RAll or release all, which is made by a work unit. And what it does is release all the locks held by the owning work unit. This is used at commit at the end of processing, where you don't want to go through and make, if you have 200 locks held, you don't want to make 200 calls to the lock manager individually to release each lock. The release all call releases all the locks held by the owning work unit. And there's change, which transfers lock ownership from one work unit to another. An example of when change is used is in FastPath. At commit time, the ownership of the locks on altered CIs that are going to be written out is changed from the dependent region to the output thread iTask, so that the dependent region can go on and do the next unit of work, and yet the CI remains locked until it is successfully written to the area data set. And notify, that's an IRLM only function, and it's messaging. The way it works is that partners obtain a shared lock on the same lock name. The lock doesn't have to be a database name or a segment or anything. The lock name is totally arbitrary, so long as all partners get this share lock on the same lock name. And then the notify call takes the lock token from that lock as input, and it's sent to any IMS, any database manager that has interest in the lock name. That is, who owns a share lock on the same name. It's used for things like dataset extend notifications, syncing the DMAC and FastPath when an update is made on one system. Sometimes, for example, with SDEPs, it needs to be made on other systems. So it's used for that. It's used for things like shared VSO, for unload command processing, utility processing. And for full function, of course, the main use of it is for extending a data set. When a full function data set is extended by one IMS, the other systems need to know about it. It's also used for global commands, global DBR or global start. All IMSs get a share lock on a command, an arbitrary string that's the command lock token. That enables them to pass commands between IMSs. So inside the IRLM lock structure, there are lock table entries. There's one entry per held lock, and it's a 2-byte entry. And if you recall, when you make a lock request, you need to hash the variable length lock name to a 4-byte value. That hash value is used to determine the lock table entry. And that way, IRLM can quickly go to that table in the coupling facility, determine if it's empty or not. And if it's empty, the lock can be granted immediately. If it's not empty, that potentially the lock is held. And at that point, IRLM has to look and determine if, in fact, it's a hash collision and a synonym to the same for different locks to the same lock table entry, or whether or not it is, in fact, a lock on the same lock table string. At that point, XCF communication between IRLMs has to happen. Record table entries. There's one entry per a modify lock. A modify lock is a lock that represents altered data. And it's important because it's a lock that has to be kept and retained if the database manager fails, right? And it also must persist if IRLM fails. So that lock is maintained in the lock structure in the record table entry. Not all locks are modify locks. Even exclusive locks are not modify locks. For example, in FastPath, a lock is changed to be a modify lock only at commit when the data is going to be written out. The division of structure inside the space, or division of space within the structure, is set by the LTE equal parameter on the IRLM procedure. And that partitions the lock structure into lock table entries, record table entries. We recommend that you use the online CF sizer tool to initially size the lock structure. And each IRLM keeps its own locks in 64-bit private storage. So every lock that an IRLM requested, even if it's a modify lock or a lock that's going to end up in the coupling facility structure, is also held in its 64-bit storage. This means that if you lose the coupling facility structure and you get all the IRLMs remain active, across all the IRLMs, we have a complete picture of all the locks in the sysplex, so the structure can be rebuilt. So if you lose the coupling facility lock structure and all the IRLMs survive, the lock structure can be rebuilt in another CF. That's why it's important to make sure that, from a configuration point of view, that you don't have a KEC that has both a CF LPAR with a lock structure in it and a ZOS LPAR running an IRLM that uses that lock structure. Because in that case, if you lost the KEC, you would lose both the lock structure and one of the IRLMs, and you would not be able to rebuild the lock structure. Okay. So going back to the hash value and then remember the hashing is done by the database manager when it makes the lock request. That 4-byte value. If the slot's free, the lock can be granted immediately. If the slot's not free, then the IRLMs have to exchange the actual lock name via XCF. If the lock's actually held, that is, the lock name of the requester matches a lock held on another IRLM, then it's actually held and the requester has to be suspended or given a bad return code. It's a conditional request. If the lock's not actually held, it's false contention. That means 2 different lock names, strings, hashed to the same value. So in that case, the lock can be granted. And false contention can happen because of too small of a lock table or a poor database manager hash routine. And there have been cases of both IMS and DB2 having what you might describe as poor hash routines. But it's not easy or safe to change a database hash manager hash routine because it's very important that all database managers use the same hash routine such that a given lock stream hashes to the same value. If that didn't happen, then you could potentially be granting requests that should not be granted because in fact the lock is held. So it requires, if you change the lock hash routine, it requires all systems restart, and it's very important that everybody is using the same algorithm. For that reason, those hash routines don't change very often. So IMS and IRLM interaction, when IMS connects to IRLM, that's called an identify. One of the things IMS passes is the address of a suspend routine and the address of a resume routine. So when a lock request is made, a program call instruction is made to IRLM. So that means the dependent region TCB issues a program call instruction, which switches address spaces and starts running code in IRLM. If the lock can be granted, then it's granted. The necessary updates are made in IRLM storage into the coupling facility, and the lock token is returned. If the lock can't be required, it can't be granted, and a suspend is required, then the suspend routine is called under the IMS dependent regions TCB. So the TCB program calls to IRLM. IRLM checks to see if it can give you the lock. If they can't give you the lock, they branch into the IMS suspend routine, and the suspend routine does an IMS dispatcher service call and ISR wait. So that suspends the request. When the lock is granted, the IMS resume exit is driven in SRB mode, and the SRB will IPost the PST that's in the ISR wait, and the PST will get redispatched inside the suspend routine. It will return, the suspend routine will return to IRLM, and that will return back to IMS with the dependent region with the lock token of the granted lock or the return code. Now, deadlocks and long locks. At identify time, IMS passes 2 other exit addresses: the address of a deadlock routine and the address of a long lock routine. And IMS also passes a timeout value. This happens, the timeout value is passed whether or not you're using lock timeout in DFS VSM XX. If you're not coding it, IMS passes 300 seconds or 5 minutes. If lock time is coded, the smaller of the value coded for BMP or message is passed. And as we'll see in lock time, if you're going to implement lock time, you can code different lock time timeout values for message-oriented processing and batch-oriented processing. So deadlocks. On a deadlock cycle, there's a parameter on the ILM procedure called deadlock equal XY. X is the local deadlock detection interval. If you code a value between 0 and 99, it's considered to be seconds. If you code a value greater than 99, it's considered to be milliseconds. It's interpreted as milliseconds. And Y is obsolete. It's the number of local global detection intervals per global interval. It used to be that IRLM would look for local deadlocks at a different interval than it looked for global deadlocks, but that's no longer true. No matter what is coded, one is used. So at that specified interval, that time interval, IRLM checks for deadlocks. And if a deadlock is found, it calls the database manager deadlock exit. So for IMS, it calls DFS DLK X0. And the exit is passed information on locks involved in the deadlock. And the DBMS exit instructs IRLM on the action to take. So in the IMS case, we always return instruction to reject the lock request. And beyond that, we return weighting values for the participants in the request so that based on those weighting values, IRLM will select the deadlock victim. Or the exit could say do nothing and leave the deadlock there, but we don't do that. So what happens when it's called? It gets storage to save the deadlock data. It saves the address of the storage in the victim PST, the one that's going to abend, in the victim PST. We know which one that will be because we know the deadlock value. We know the weighting values passed to it. And then we instruct IRLM to reject the request and we return to IRLM. So then IRLM returns to the lock requester with a deadlock rejection return code. Inside the IMS code that actually made the lock request, the lock manager, DFS LMGR0, it sets up a 777 abend in the PST, and it returns to the DLI call handler, and the call handler issues the 777 abend back on the other side of the PC instruction, back in E8 application code. And then when abterm processing runs, it uses the saved deadlock value that was saved by the exit, and it produces 6-7 Fox records to document the deadlock. So that tells you the lock name and the participants, etc. And if it's a message-driven flow, the input message will be requeued to be retried. So for long lock processing, now long lock processing happens during the deadlock cycle. So during the deadlock, each deadlock cycle, IRLM looks at every lock that's waiting and compares the time it's been waiting to the lock time passed by the database manager at Identify. If it's been waiting greater than the lock time, it calls the database manager long lock exit, and it passes information on the waiter and the blockers. And the long lock exit will instruct IRLM on what to do. And the options there are to do nothing, which means continue the wait, or you can tell IRLM to reject a request with the timeout return code. So the implication of that is your lock time value should be an integer multiple of your deadlock value, right? Because, for example, if you have a lock time of 10 seconds and your deadlock value is 3 seconds, we're going to look for long locks at 3, 6, 9, and 12. So the lock would not actually time out until 12. So that would be 2 beyond the 10 you coded. So you definitely want it to be an integer multiple of the deadlock value. And remember that deadlock might be in milliseconds. Lock time is always in seconds. So if lock time is not coded in DFS VSMXX, IMS will pass 300 seconds to IRLM as the lock time. And we don't set any flags inside of IMS to say that lock time is active. If lock time is coded, we pass the smaller of the BMP or message value to IRLM as the lock time. And we always pass the address of DFS LOKX0 as the long lock exit. So what happens in IRLM when their deadlock cycle process detects a long lock that's been waited longer than lock time, it calls DFS LOKX0. Inside of LOKX0, if lock time is not active in IMS internally, so that is you did not code lock time, So that means the timeout value was 300 seconds. We write SMF 7915 records that document the waiter and the blocker. And then we return to IRLM and say continue waiting. If lock time is active in IMS, we determine the waiting region type, whether it's batch oriented or message oriented. And then we compare the message value coded to the actual time that the request has been waited. If it's exceeded, we write a 7915, potentially build a DFS 2291 lock timeout message and save the address of it in the PST. And then we set a return code to IRLM that says reject the request as a timeout. So in that case, IRLM returns to the lock requester with a timeout return code. The lock manager interface in IMS sets up a 3310 return code, or optionally a BD status code, because you don't have to request an abandon a lock timeout. You can request a call status, a BD status code. You better be really careful if you request that. You better make sure that your applications check for a BD and understand that the call did not complete if they get a BD. Optionally, the lock manager will issue the DFS 2291I message. There's a parameter in DFS DFXX, message 2291 equal, issue or short. That if you have that coded, it will issue the message that identifies the waiter and the blocker. You can potentially automate on that message to AB dump the blocker if you so desire. A fairly old APAR there adds a subsys to the short form of 2291. The difference between the short and the long form is it's a single line WTO in the short form. It's a multi-line WTO in the long form. And it's much easier for automation to deal with a single message than to deal with multi-line, because then it has to correlate data between instances of ZOS WTOs. So an important concept here is that there's two lock times. There's IRLM's value, that's the value that IMS passes to IRLM and identify. And then IMS has values for batch-oriented and message-oriented. And both of these can be changed dynamically. You can modify, with a modify command, you can change the IRLM timeout value, and you can change IMS's values with an update type 2 command, update IMS lock time value. So again, the IRLM value should be an integer multiple of the IMS values for the same reasons. For example, if you had a message timeout of 10 seconds and you set the IRLM lock timeout value, the overall IRLM value, to 12 seconds, then obviously it's going to wait 12 seconds before you time out and not 10. Or if you coded 3, it would also wait 12 seconds, because it would be 3, 6, 9, 12, right? So the message and message-oriented and batch-oriented timeout values and the IRLM values should be integer multiples of each other. So a little known function here is even if you're not using lock time in IMS, you did not code it in DFS VSM XX, you can reduce the IRLM value to collect SMF 7915 records to analyze performance issues with a modify command. So if you're not using lock time in IMS, you can issue the FIRLM command and change that 300 seconds, which is, I mean, if a lock is waited 5 minutes, you've probably got a very large problem. You probably want SMF records well before that time. Maybe you want them at 15 seconds or 10 seconds or something. You can issue a modify IRLM command to change the timeout value to 10 seconds. That does not turn on lock time in IMS. All it does is change the interval at which SMF records are produced. And because it's a command, you could potentially do it at specific times, or while you're having a performance problem, you could reduce the timeout value so you could get SMF records describing the conflicts. If lock time is active in IMS, then you shouldn't mess with the IRLM value, because the SMF 7915 is only produced when the IMS time is exceeded. So how do you interpret these SMF 7915 records? If you have RMF, the RMF iLock all command gets the SMF records from the buffer, SMF buffers in the running system, and formats them in real time. I think most people have OEM monitors like MainView or Megamon that probably do the same thing and present it better. So I don't really recommend the iLock command. But post-incident, because the fact that the SMF records were produced, you can format these records with the IMS PI, Problem Investigator tool. Other vendor tools format these records. You can use your own, you can write your own program to do it. There's a mapping macro called ERB SMF that maps the 7915 records. Or, I mean, realistically, these records are not difficult to interpret. They're pretty straightforward. You can print them with ID cams and just eyeball them. And there's a DFS SMF 79 dissect in the source of DFS LLKX0, which can be used to format the records. So other locking considerations. Lock max, that's an IMS parameter to limit the number of locks a dependent region can obtain. Even IRLM and 64-bit storage can run out of space, right? And it can certainly run out of coupling facility structure space, probably before it runs out of 64-bit storage. And even if you don't run out of storage, having too many locks can cause contention, running long lock change can cause performance problems, etc. You probably do want to limit the number of locks a particular dependent region can have. A lock max is a dependent region JCL parameter, or you can code it on PSBGen. Unfortunately, there isn't a global system-wide parameter. So if you go back and think about it, for a message region or a batch region, you can code it on the dependent region JCL. But if you're using DB control or ODBA, ODBM, ODBA, the only way to set the lock max is to code it on PSBGen, unfortunately. Locking statistics. Now, how would you know what value to code for lock max? IMS records the high watermark lock count of locks held in various commit records, 37, 38, FastPath 59, 37, 38 records. And IMS PA will report on them. They're also in the 5.6 FA record, I believe, if you have transaction level statistics turned on. The high watermark count is not the same as the number of lock requests made, because locks can get released during a commit cycle. As PCB position moves forward for full function, locks on unaltered data can get released. For FastPath, when you hit NBA and buffer steals invoked, locks on unaltered buffers are released. So high watermark count doesn't reflect total lock requests. There's a V14 PTF that added lock request counts to the 5.6 FA TLS records. To get that, you have to have TLS turned on, transaction level statistics. You can turn that on system-wide, or you can turn it on a transaction basis. It supports both PI and IRLM. And what you might use with that is just identify opportunities for proc-opt equal go. You can identify BMPs or even transactions that make a lot of lock requests, but potentially are proc-opt G share requests. And they're potentially candidates to use GO and read without integrity. Often, if you have a true GDPS or a campus environment where one system is closer to the lock structure than the other, it may make a difference in terms of number of lock requests, minimizing lock requests. Okay, so that's about it. I hope there's something useful in there. Any questions for me?
Yeah, so what I'd like to do is unmute everybody. So you're welcome to still post a message in the chat, or if I basically request everybody to unmute themselves, that should basically mean that that they should be able to ask a question. But just aside from that, just bear in mind that we've got video recording of this session, and that video playback will be available at some time in the near future. And I'm presuming, Kevin, that you will have slides available, so that
I'll send them to you.
Yeah, so they could be loaded up and they'll be available as well. There are feedback for this session, so we haven't got the QR code in front of us, but basically if you go on the agenda on the GSE website, if you just click on this session in the agenda, then it actually gives a link. So if you click on the title, Nuts and Bolts of IMS Lock Management, then it will actually give you a link to do feedback for this session. So, I mean, I've got a question just on that PTF that you were talking about just at the end, the UI 47337. So that's to put an extra information on the 56 FA records. Is that likely? I mean, it probably depends on how many locks you've got. So and transactions, is it quite a big overhead to switch that on?
There's no overhead because the data is collected whether you record it or not.
Okay.
It's a total, right? So like all the other, for transaction level stats, turning it on really only involves the overhead of writing the log record. The statistics are collected and maintained regardless. The turning it on just goes through the overhead of writing the log record at the end.
Okay, yeah. And I mean, I've got another question on when you were talking about the database hash routines. What did you mean by that exactly?
Okay, you're thinking of, if you think of a randomizer.
Are you talking about the randomizer? Yeah, this is what I thought.
No, I'm not talking about the randomizer.
No, but this is what I thought. You're not talking about that.
No, I'm not talking about the randomizer, but it's conceptually similar to a randomizer. Imagine it as a randomizer for the coupling facility.
Yeah.
It takes the lock name and hashes it to a 4-byte value, which, instead of a randomizer takes a key and hashes it to a wrap number and an area number. The lock hash routine takes the lock string and hashes it to a lock table entry number.
Okay.
It hashes it to a 4-byte value that is then, processed by RLM as a LTE number, right?
Mm-hmm.
So it's for the same reasons that everybody needs to use the same randomizer when they're accessing a database. Then everybody using the same RLM had better be using the same lock hash routine. And there are different routines. FastPath has a different routine than full function does.
Okay, so basically what you're saying is there is a way from the installation point of view of actually changing that, but it would be quite a widespread change to do if you were going to do it. And I guess
there is a way of changing it for FastPath. I don't know that there is a way to change the full function one, but don't ever do it.
No,
don't ever change it.
No, I wasn't thinking of doing that. And it was just an interesting comment that you made, and obviously you mentioned something about the lock table size is also important. So that those things can be changed, the actual size.
An example of that is until version 12 for FastPath UW locks, that is for high-speed reorg and HSSP, the hashing routine had a bug, and it was always passing 0 as the hash value. So every UAW lock hashed to the same LTE and went through false contention. That was fixed in version 12, and there was some cleverness in the looking at some DMAC flags to make sure that are synchronized across systems to make sure that everybody was at the right level. But it has, and DB2 has the same, DB2 uses the same thing, and I'm aware that DB2 actually has a few issues in this area too, because we've been looking at ways to address all of them.
Yeah. And then my final question was just on the normal U777 bands. They are expensive in the region, because it has to do the big overhead when it comes back in, and we should be at war with them on those, because from our shop, we do still get quite a number. So we're still going through those as something that we target.
Yeah, my argument is always that if your reason that you can't convert to IRLM is because of deadlocks, maybe you have a bigger problem and you should fix the deadlocks, right? Because just continuing to use PI because it detects deadlocks faster is not optimal.
No. Okay, so we've got any more questions for anybody? Please unmute yourself and don't be shy.
I've got a question. It's not it is block related, but not kind of what you've gone over today. If you've got a transactional workload, is there a way to free the locks in a unit of work? I think the answer is no, but I know
there is actually.
Okay.
Isn't there a call?
There's a DQ call.
Yeah, DQ.
It's obviously you can't free locks on altered data, but you can issue the DQ call to release basically non-necessary locks.
But that's only on non-up. So you couldn't commit the locks, any updates, and continue the unit of work fundamentally.
Within a message driven, obviously you can within a batch process, right?
Yeah.
You can't within a message driven process.
Okay. It's just because Kix has a way to do it, and just had some people asking about it, so I was just curious.
Well, Kix doesn't have message integrity, right? The IMS idea is message queue interactions are part of the database interactions, and it's all or nothing, right?
Yeah.
Through the same commit scope, right?
Yeah. Okay, thank you.
So any other questions? We've got another sort of 8 minutes to go for the end of the session, so don't be shy if you've got any more questions. I mean, I've got another one, just to, in terms of, I think what you'd saying before about when you're doing the setup of the coupling facility structure, I think you were saying that's got to be, you were talking about the KEC.
Right.
So can you explain a bit more about that again, just to refresh what you talked about there?
Well, say you buy a Z, we'll refer to a particular Z15 as a KEC, right?
Yeah.
And it's usually got multiple LPARs in it, right?
Yeah.
And one of those LPARs might be a coupling facility, an internal coupling facility, right?
Yeah.
So if you do that, you want to make sure that on that Z15, because the Z15 itself is kind of a unit of failure, right? It's possible that the whole thing fails and all the LPARs in it fail, right?
Mm.
So you don't want to have a ZOS LPAR with an IRLM in it and a coupling facility LPAR implementing a lock structure that IRLM uses. Because if you lost that Z15, that CAC, you would lose both the structure and one of the IRLMs that uses it. And to rebuild the structure, all the IRLMs have to survive.
Okay.
If that does not happen, then if you lose one IRLM and you lose the structure, then you're going to be shutting down the surviving systems and restarting them, doing an all systems warm start of them.
Yeah, I get that now. Thanks.
And that logic applies to DB2 just as well as IMS, right? The DB2 lock structure has exactly the same considerations, and I think their global buffer pool has the same consideration. So normally what you would do is people buy, that's an argument for buying an external coupling facility, right?
Mm.
So it's in a separate box, isolated from the IRLMs.
Okay, that's great. Thanks very much for that clarification. So have we got any more questions for Kevin? And the other thing to say is when you do the link for the feedback, there's also you can vote for when you do that. Basically, there's some charity that we're supporting for this year, which is the one of them is the I think National Knife Boat. So please encourage you to do the feedback forms, which, as I said, if you go into the agenda of the GSE website, you just click on the link basically click on the title of this session, which is nuts and bolts, and then that will then provide you with a link to do the feedback. So I think if we haven't got any more questions, then we'd just like to thank you very much for that session, Kevin. It was worthwhile. We had about 60 in total, I counted about 16 people, 17 people at one stage. So well attended and much appreciated. And as I said before, we've got the video recording that should be available soon, and the slides will be available for people to read afterwards as well, once those have been given. So I hope you have a good rest of your conference, everybody. The next session for IMS stream is it's as I described the color coding on the sessions on the agenda. It's the avocado, or is it grey green, whichever you'd like. But if you could, the next session for IMS is 12 noon on the 4th of November. So thanks everybody for your attendance, and thanks Kevin for doing that really worthwhile session.
My pleasure. Thank you.
So round of applause virtually, please.
Okay, thank you. Okay, bye.